Okay, so in this one we're going to consider the relationship between the Dirac delta function and the Fourier transform that we talked about last time. So to begin, let's consider a sequence of equally spaced delta functions. So we'll put one right at the origin, and then every L units we'll put another one in both directions off to infinity. So this would be delta of x, this would be delta of x plus L, and this would be delta of x plus 2L, and so on in both directions. And this is a periodic function. Of period L. And since the delta functions are zero, except at one very specific point, to construct this function, we can just sum all of these delta functions together. So we could write, delta of x plus delta of x minus L plus delta of x minus 2L, and so on. Or as a sum, I like to use Q. Or I guess I should say that Cohen-Tannoudji uses Q. But we can write this as x minus QL. Okay? So this is what that function can be represented as mathematically. And when we have periodic functions, we can write them as Fourier series. At least that was the promise from the last few lectures. So remember, if we wanted to write the Fourier series for f of x, then we would write it up as a sum over n, where n is an integer, of these, with the phase convention, right? I k sub n x, so these harmonic functions times some amplitude or some coefficient. And here we have kn equals 2 pi over L times n for n integer. Q is an integer too. And so if we want to write this function as a Fourier series, our task is to determine these coefficients C sub n. And we have a formula for that. The coefficients are given by 1 over L integral over 1 period L. We can start anywhere we like. With respect to x, e to the minus I knx, and then the function f of x that we wish to represent as the Fourier series. So yeah, this integral, the bounds must cover one full cycle. We could start at arbitrary x naught, but let's choose a symmetric window, plus or minus L over 2 dx e to the minus I knx f of x. So we are integrating from here to here, and within this window, actually only one of these delta functions is non-zero. It's the one given by delta of x. So that's important because when we write out f of x, as a sum over Q, the original representation, this infinite sum of delta functions, when we're integrating over this small window, is all of these delta functions give 0 except for the one centered at 0. So this sum basically collapses to just a single term, and that's not collapsing because of some property of the delta function other than the fact that all of the action is located at a single point. So we have only the single contribution of delta of x. And we know how to evaluate this now. The delta function just acts to pluck out a single value of the inner function f of x here, f of x. So we can just substitute in, so the integral collapses and we sub in x equals 0, and so we get e to the minus I kn 0, which is just 1 over L times 1, so this gives 1 over L. So each coefficient in the Fourier series given here is equivalent and equal to 1 over L. So Fourier series for this periodic sequence of delta functions is just from this formula here, 1 over L sum on n e to the I k n x. So the observation is that if we focus our attention within just this window of L over 2 for a second, we see that a narrow peak, a delta function, centered at x equals 0, results from a superposition of harmonic waves. These guys are the harmonic waves. We're doing an infinite sum of them in a linear combination, which is a superposition, of equal amplitude, in this case 1 over L, and all of them being in phase at x equal to 0. This yields just a very sharp peak located at x equals 0. So basically all of these waves are adding constructively right at x equals 0 and interfering with each other everywhere else. So you get only this big spike at x equals to 0. Okay, so now let's recall the Fourier transform. So we have the pair of functions f of k, the Fourier transform of f of x, being 1 over 2 pi integral minus infinity to infinity. This is a function of k, so we need to integrate with respect to x of e to the minus I kx times f of x. This is the Fourier transform of f of x. And then the inverse